Hello? Anyone? Can you say in the chat if you can hear me, maybe? All right. Oh, amazing. Thanks. Okay. Cool. Yeah. We're live from Balboa Park, San Francisco today for strange reasons. But yeah, I have all the slides ready to go. And let me put the link in the chat too. Okay, so that's the link to the materials. But then if you want to go right to the slides, it's sec. That should work. So let me open that and then I'll screen share. No. I know I haven't. All right. Give me 30 seconds and the slides will be ready. Sorry about that. I named a file wrong. It does not work. Right. Oh, no, I just typed it wrong. It was working. Okay, one more try. Sections, plural. Gosh, 07. Okay, the one I just typed? Yes, cool, it should work. So let me screen share and we'll learn data science. All right. Cool, screen share. Week 7 slides. Cool. So welcome. Today, Python functions, control flow, law of large numbers. So functions, you know what those are. Control flow, you learned in lecture and you'll learn what that is, but you know, those are the two Python things today. And then law of large numbers is stats, but you'll see, like, in a weird way, you'll learn more Python by doing law of large numbers stuff probably than just even like learning functions and control flow directly. So yeah, let's get to it. All right, cool. This is it. Yeah. So yeah, Python for the first half and then not Python for the second half. Cool. Functions. Yeah, we like started functions 2 weeks ago, or I guess like 3 weeks ago, 2 labs ago. And the thing about functions that you want to remember is that like actually you have seen functions kind of from the jump, kind of from like when we started learning Python, because things like print, right? Things like float, right? The conversion functions that we learned, they're all built-in functions. So those are to me like the most, you know, basic first ones that you learn because you don't have to do anything. As long as you're like coding in Python, like whatsoever, as long as you have Python on your computer or on Jupyter, you know, on NYU server, these functions are always available, right? So print, it will just display something. The conversion function, yeah, we learned those. So hopefully you get that. As a refresher, like the syntax is the name of the function, and then parentheses, and then arguments to it. So in this case, print takes one argument, which is like the thing you want to print out. Float takes an argument, which is the thing that you want to convert into a float. And then remember that you can like nest these. So, you know, you can take, in this case, we're taking the outcome of float parentheses string infinity, and we're finding the type of it, right? And it shows us float. I included this to show you that, like, you know, I could have done like float and then like quotes and then 13.738 or something, you know, a normal float. But I just wanted to show you that float also has this infinity value built in. And you could even do like negative sign float infinity, and it would give you negative infinity. Just so you know, that's how you get infinity in Python. So, and yeah. When we learn while loops, we might learn a reason why you might want to have the numeric like infinity variable. So cool. Imported functions though, right? Eventually you hit a limit of things that you're trying to do with normal standard Python, and you just get like, hey, Python tells you, hey, I don't have this function, right? So in this case, I made a list of numbers, and I want to sum it, but yeah, there's no built-in like .sum function in Python. So you might, you might be in a pit of despair because you're like, how will I ever sum the numbers in this list, right? Bam, importing functions, right? That's like really where like most of the stuff that you'll do in Python is, right? Meaning Python was built like 20 years ago as like just a really bare bones language that like holds variables and like adds numbers and stuff, that lets you write functions. But like for data science, since it's not the same as coding, right? Since you're doing statistics and data set manipulation stuff, pretty much everything you're going to be doing is like, you're going to import something, NumPy, pandas, whatever, and you're going to use functions from it, right? So in this case, we import NumPy as NP. Now we have these new functions we can learn. One function is just np.array. That's the conversion function from Python lists, right? Remember my list, the last slide, is just a regular Python list, but we call np.array, that's a function, right? Imported from NumPy. And we give it my list and it converts it into a fancier NumPy array. And now that array, my array, we can call .sum on it, right? Cool, problem solved. So that's kind of the stage two, right? Like stage one is you think like, does Python have a built-in function for what I want to do? Stage two is you say, okay, well, maybe Python doesn't have one, but so there's some library easily available that does like NumPy or pandas. And you check that, but if there's neither a Python built-in function nor an imported function that you can use, right, then it's time to make your own functions. And that's kind of like where we got to in lecture this week. So the first most basic type of function is just a function like this. I called it how many letters. This parentheses is because it doesn't take any arguments, right? So the syntax is like you write def, def, that's short for define. And so that's, you're telling Python, I'm about to define a function, right? And then you say the name of the function. The underscore thing, like how underscore many underscore letters, is kind of weird because different programming languages, the style is different in terms of whether you want to use a like underscores to separate words, or do weirder stuff like capitalize the first letter of every word. In Python, there's technically like an official Python style guide that you can look at. I think it's called PEP 8 or something like that. You can Google it, Python style guide, and you'll see like, yeah, in Python, just for consistency, so that like someone looking at your code can quickly figure out what is a function and what is a variable, whatever, it wants you to use underscores. So how many letters, we separate the words with underscores. And then in parentheses, after the name of the function, we say what arguments it takes, right? In this case, none, but we'll see some that take arguments later. And then you do a colon. That's this little 2 dots guy. And everything indented after that colon, like every indented line, Python will say, okay, that's the body of this function, right? Those are the lines of code in this function. In this case, function only has one line of code, right? And what it does is it has this return statement. That's kind of the key thing that separates a function from just like random code in Python, right? Is that a function is made to be like you can think of it like a black box, if you know that term. It's like a machine, right? Like a little robot or something, and you input things into it. That's the arguments. And then return is like what that box spits out, right? So in this case, the box is called how many letters, and we run it, like click run on it when we want it to run, and it outputs the length of just a string with all the letters in it, all the English Latin characters, right? So this is just a string typed A, B, C, D, E, F, G up to Z, and then I find the length of it, right? If this was like a real class, I would be like, len, what is that? Is that a Python built-in function, imported function, or a function that we wrote ourselves? But the answer is it's a Python built-in function. Len tells you how many things are in the sequence, right? We learned before, a string is a sequence because it's like there's a first letter in it, a first character in it, a second character, third character, and so on. So Python recognizes it as a sequence. And then when you type len, that's short for length, and it's how many things are in the sequence. But note that like I write this and then I run this cell, but nothing happens, right? There's no output. And that's because a function, like we learned before, is just a block of code that just sits there. It doesn't actually run. It waits for you to call it, and then it runs, right? So we then have to write a second cell that actually calls it, right? How many letters? We give it in parentheses the arguments. In this case, there are no arguments, so it's just empty. And it gives us 26, right? And one thing I really want you to get in the habit of, because it's one of the most horrifically confusing things in Python, is that I want you to get into the habit of like, if maybe, you don't have to do it every time, but I want it to be instantly like in the back of your mind that this is a thing you can do for sanity checks, is you can take the result of the function call, right? So in this case, how many letters, call it, and you store the result in a variable called fn_result, and then you print it, right? And so that's probably like what you should do more than just calling functions in cells, you know what I mean? Because you call the function in a cell and it gives you 26, but you don't actually know technically, like, did it return the float 26? Did it return the int 26? Did it return a string 26? Did it return some other fancy thing that just happens to display 26? What you really want to do is you want to have the output of the function stored in a variable, because then you can print the result, right? But you can also look at the type, right? And in this case, the type is int. So we see like, okay, I called how many letters and it gave me an int, right? It produced an int. The reason that's important is because this is like the bane of a lot of Python coders' existence, is that you can write a function and it doesn't return anything, and you might not even like notice. So here, there's a function called say hi, right? And it just has one line, and it just prints the string hi, right? So you call say hi, and it prints the string hi, as you'd expect. But it's actually like not the exact same type of thing at all as this, right? Here we called how many letters, and it gave 26. But not because there's a print 26 somewhere in the function, right? It's just because that's the value that it returns. In this case, it doesn't return a value, it just prints hi. So if we check what this function returns, right? We call say hi, store the result in hi result, and then we print hi result. It's not like hi, it's not a string that says hi, it's actually just none, right? Type is none type. And that's because if you don't put a return statement, Python will just return this value called none, which is literally like a special Python value that's just absence, right? It's just like void, null, nothing. Meaning like this function didn't return anything. So if I store the result of it in hi result, it's just none. Hi result is none, right? And so what you should really do is like, you should make a function called return hi, right? And then it actually returns something, right? It'll still print out hi because of Jupyter printing out the result of the final line of your cell, right? But you can store it in a variable, and then you can see like, oh, now I have this string. Hi result, it says hi in it, right? It's a type string. Yeah, it could just get really confusing because like you'll write a function and you'll print out like, you'll like say like print, the answer is 5 or something, right? And then you'll try to take the output of that and put it into a new function. But if you write it like this, you're not gonna be able to do that, right? Because it returns none. It produces the value none. In this case, your function actually produces the value hi. So then you can take that output, that function, and you can like plug it into new functions later on. Hopefully that makes sense. The point is just like, if you just put like a print statement and not a return statement in your function, you're not returning anything, and so you can't like do anything with the result of that function call once it's done, right? Whereas if you return a value, right, your little robot, your little machine, like outputs a value that you can then use, right? You can say, oh, what did that function return, right? So I know it's horrible, but I had to make this to kind of drive the point home. You know, I kind of hate when my teachers make memes, but it's a visual, like just keep this in your head and you'll remember, right? Like printing stuff and not returning anything is bad. It's this guy. And then if you return things, you're looking like this, right? Because now you can take the output from that function and use it in later cells and later parts of your code and so on, right? It's not like a rule, like you're obviously allowed to write a function that just prints things, but yeah, when we start doing data science stuff, like you really are not going to want to do that, because you'll be writing a function like, oh, compute the average test score or something. And if you just print the average test score, then you can't like have code that, like, say you have like you have 3 data sets, it's 3 classes, and you want to compute the average like test score for each and then find the average of the averages or something like that. Let's say we're doing that. If your function just prints the average score, right, you're not going to be able to take the 3, like you might call like find average score class 1, find average score class 2, find average score for class 3, right? But if your find average score function doesn't return anything, then you can't take the average of those averages, because it just printed something out to the screen. It didn't actually generate an int or a float value, right? So cool. I really hope that makes sense, because it's fine. We'll run into it in the future. You'll like probably accidentally write a function that just prints something instead of returns something, and then try to use the value, and it'll just be like, it's none, right? Like in the class example I just used, technically like compute average score, it will return none for each of the 3 classes, right? It'll print the average score, but it won't return anything. It'll return none. And then when you try to take the average of the averages, it'll just be like, all right, it's none also. The average of 3 nuns is none. Cool. So yeah, and you can make your own parameters too, right? So just like how the print function takes a value, takes a parameter, you can write your own functions and take parameters. Sorry, I should say one last thing. The return statement is not a function. It's very weird, right? See how print, we have these parentheses around it? Return, there's no parentheses, because it's a like very unique like Python syntax, where you just put return, and then whatever comes immediately after it, that's like what your function returns. Technically, you can put parentheses. It's just, I want you to remember, return is not a function. It's called like a command in Python. It's very weird, and I'm sorry, right? But just notice like the parentheses here, print high, but no parentheses on return high, because print is a function, return is a Python syntax. Yeah, Python command. Cool, and you can make your own with parameters, right? So whereas before we wrote def and then the name of the function, and then we just had like open parentheses, close parentheses, and the colon. If we want parameters, we just put a list of the parameters separated by commas. So in this case, we only have 1 parameter, so I didn't, but we'll see. Yeah. So in this case, there's 1 parameter, we'll call it the number, right? What that means is that like when you write this function, inside the body of the function, right, inside the indented lines, you can use this variable called the number, right? Meaning you're writing it and you're like, okay, so whoever's calling this function is going to give me an argument, a parameter called the number, and then I'll be able to use it. So in this case, we multiply it by 3 and we return that result, right? And then we can call it, we can say triple, we give it 5 as the parameter. It returns 3 times that, which is 15, right? Triple 0, 3 times 0 is 0, turns 0. And again, remember, we can always nest these. That's what this is called when you like have the output from a call to the function, be the input to the call to another function, right? So It's a little confusing because you have to read it from the inside out. Like it takes some, training. But what's happening here is like the innermost thing, right? Maybe that's the best way to remember or like learn this is you look for like the innermost thing, the thing with the most parentheses around it, right? The innermost thing here is 5. And it's like, okay, what's happening to 5? Well, we're giving it as the argument to triple, right? So that's this. So this highlighted part right here is saying, okay, I'm going to call triple with the argument 5. So that's going to give me 15. We saw that up here, right? But then we're going to take that 15, right, that result, and we're going to plug it back into triple again. So then it's going to triple 15 and it's going to get 45, right? So hopefully just stare at these for long enough and it'll make sense. Sorry, there's an emergency. Hold on. Chat. Okay, cool. Hopefully people can still hear me. There's a lot of emergencies happening because the world is burning. But hey, we're chilling. Yeah, and this is just to show you can do more than one, right? The thing I mentioned where you separate them with commas. So in this case, I wrote a function combine names because I wanted to show you like triple is a function that takes in a number, right? And it returns another number, but you don't have to, your functions don't only have to deal with numbers, they can deal with anything. In this case, we'll take in 3 strings and we'll combine them, right? So first name, second name, third name, and it'll just put commas between them and do the Oxford comma and say and, right? So you can stare at this for a little bit, but the point is like, you just have your return and then all this is what it returns. And so it takes the first name, right? And then we remember that the plus sign when you're working with strings means concatenate, so add to the end. So we take the first name, then we add comma space to the end of it. Then we take second name, add it, or concatenate it, sorry. Then add comma and concatenate that. And finally concatenate the third name, right? So if we call combine names, we can send it 3 strings, right? In this case, Alice, Bob, Craig. And it gives us a string that combines these 3 separate parameters, right? In this case, it makes 1 string that's Alice, comma, Bob, comma, and Craig. I actually, yeah, in case you're wondering, like Alice and Bob, that's not just like random names I made up. It's like a thing in computer science, especially cryptography that, yeah, long story short, you can read this Wikipedia article, but like, if you want to study computer science or like data science, especially security, you'll want to learn the names Alice, Bob, and Craig. It's a sidebar. In cryptography, Alice is like a person sending a message, Bob is a person receiving a message, and Craig is a person trying to intercept the message. So now you know. Cool. Yeah, so now we're doing conditional statements, right? Control flow statements. Well, okay. Both loops and conditional statements are control flow statements. The reason they're called control flow statements is because, yeah, until now, if you notice, every time you ran a cell, right, you put Python code in a cell and you clicked run or did shift enter, command enter, it just ran the lines one by one, right? You had no way of saying like, actually, wait, don't run this line. Well, you did by commenting it out, but you didn't have a way of like programmatically saying like, oh, run this if the user typed in yes, or run this other thing if the user typed in no, or something like that, right? But now we're learning control flow statements, which is how you actually control, like, it won't run all the lines, right? It'll check certain conditions using if else, or if else, we'll learn about those, but it'll check certain conditions and it'll only run code blocks you write based on whether the conditions are true or false. So yeah, if statements, we learned those in lecture. These are just screenshots from the lecture slides, but if statement is the most basic, it's just if condition, then expression or expressions, right? I probably should have just written expressions without the parentheses, because the point is you can, you indent it and then you can put whatever Python code you want. And that Python code will only run if this thing up here is true, right? If the condition is true. So this flowchart is like a graphical representation down here because we have the test expression, right? So it first looks at this condition or test expression. yeah, sorry, I use condition, but test expression, it's a synonymous. And if it's false, it just doesn't run your code at all, right? So if the condition is false, it just goes to the next thing, or it finishes running. If your whole code was just an if statement. But if the condition is true, then it runs the indented code, right? So kind of like how we indented code over here to show that, oh, this code is inside the function. Here we indent to show that this code is inside the if statement, right? So cool. We see some examples here, like, we set some variable x equals 5, and then we say, oh, if x is greater than 4, then print x, right? And then it's kind of dumb because we know, like, oh, it's always going to print x, right? Because we set x to be 5, so obviously it's going to be greater than 4, right? But that's just like a toy example, because really what's going to happen is you're going to, write programs that are like load in a data set, and then if the variance is above 10, print like variance too high. Otherwise, print the variance is okay, or something like that, right? Where you won't know in advance what it's going to print, right? So this is just a toy example. If else is, you can actually specify something to do if the condition is false, right? Meaning, like, here, if the condition is true, it runs it, but if it's false, you don't, like, it's done, right? It doesn't do anything. If else is a fancier version where it's like, oh, it's always going to do something, right? So if the condition is true, then it's going to run this code. Otherwise, else, right? It's going to run this code. So in the variance case that I said, I guess I should have said, like, that would be more an if-else statement. Like, you would say, if variance greater than 10, print variance too high, else print variance is fine, right? So that's an if-else statement. It runs the test expression, right? Following this flowchart here, it runs the test expression. If it's true, it runs the if statements. The statement's indented below the if. But if it's false, it runs statements indented below the else, right? So, and then, yeah, we learn these as like if, else if. I like to call it if, elif, dot, 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 elif, else, because the point here is like the dot, dot, dots are, now you can include as many conditions as you want, right? And that can be pretty helpful because you might have like, maybe you have a game, right? You're like coding like a board game or something, and you want it to do different things based on a dice roll, right? So maybe you ask the user to roll a dice, and then you ask them like, oh, what did the dice come up? 1, 2, 3, 4, 5, or 6, right? So in that case, you have like 6 conditions. And there, so you would want to use like 6. You'd want to put like, say, if dice result equals 1, run this. Elif dice result equals 2, run this. Blah 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 down to maybe you get a elif base outcome equals 6, run this, and then the else in those cases is kind of weird because you're like, well, the dice can only be 1 to 6, so I don't know what to do in this else, like a 7th case. And my advice is just, I mean, this is just the thing I do all the time, but it's like you can just put a print statement or an error statement that's just like, the code shouldn't reach here, right? Meaning like maybe the user typed in like 15 and you can like give an error because you can say like, no, you have to roll a 6-sided die. Or maybe the user typed in like help and you're like, that's not, I don't know how to interpret that. I was checking 1, 2, 3, 4, 5, or 6, right? So anyway, that's the if, elif, else, right? You just like stack them. You just put if, check the first condition, then elif, then elif. And a thing to notice here is that they're gonna run in order, right? So it might be on the homework actually. There might be a question if the homeworks are like were in previous semesters, although they're really not. But on previous iterations of this class, we had like a question on the homework that was like talking about how it matters what order check if it's divisible by 4, right? If you know your math, like you'll know that second elif, it's never going to be true, right? Because already it was checking if it's divisible by 2. So if it's divisible by 2, it's obviously going to be divisible by 4, right? So you can get weird stuff like that. So when you do these if, else statements, you have to keep in mind that they're going to run in order and make sure your conditions actually make sense, right? So meaning, like, just as a general rule, the conditions should get less and less likely, you know? So that, like, the first condition is like, okay, most of the time it'll be this. Second condition, okay, it'll be like this sometimes. And then the else is like, you catch the weird cases, right? The else is kind of there typically to catch like something has gone wrong, right? Like you say, okay, first check if it's divisible by 4. If it is, then do something. Then check if it's divisible by 2, right? That order makes sense because it could be not divisible by 4, but yes, divisible by 2, right? And then you can have an else that's like, if it's not divisible by 4 and it's not divisible by 2, your else can say, oh, hey, this is an odd number, right? It's not divisible by 4 and it's not divisible by 2 or something. Or it's not a number at all, right? It could be either of those. All right, so cool. That's conditional statements. Sorry, I'm kind of rushing through this because my average has definitely been to like not get through the slides in time. So I'm trying to definitely get through the slides in time. Maybe someday we can have like question and answer at the end, I hope. Cool, that's my goal. So while loops, if you notice like that was the first control flow type is these conditional statements because you can now control like, oh, only run this code if this condition, right? Though these loops are a different type of control flow, right? Because loops are a control flow where you want it to run a thing a bunch of times, maybe like a variable number of times, and you don't want to write the same code like 100 times, right? So that's what these are for, basically. It's like, oh, I want to print all the numbers from 1 to 100, right? You can start writing print 1, print 2, print 3, but it'd get really tedious, right? San Francisco is like just really on fire. I guess I don't really live on this side of the Bay Area, though, so it seems like a lot. Anyway, while loops, we're looping, and it's just, yeah, it checks. It's kind of like the if statement if you think about it. Here, you instead of if, you put condition, you put while condition, right? What that means is like, oh, don't just run it once, right? The if statement says if condition expression, and it just runs the expression and then it moves on with the program. The while loop, right? It's a loop, so instead of just running once, it's just going to run the expression as many times as possible, right? It could run it infinitely many times. Then you have an infinite loop, which we saw in the lecture. But in this case, like, it's just going to keep running the indented code underneath it over and over and over and over again until the condition is false, right? And it's a little weird, but if you think about it, like, it could also run 0 times, right? If you hit the while loop and the condition's false at the beginning, then it just never runs the code, kind of like an if statement, right? So that's what's happening with while loops. We have a nice flowchart here from lecture, which is just, yeah, it goes around this circle over and over again, checks the condition. If it's true, runs code, and goes back in the loop over and over again. But if it's false, then it just ends and it goes to the next thing in your program. Cool. That's what's happening there. Yeah, while x is true, do y. That's what I want you to think of. That's why it's a while loop, while x is true. And so here we make some variable I. If it helps, I is like short for index here. Like in general, in like Python and in coding, like I is typically reserved for an index, right? Like your index, like 0, 1, 2, 3, 4, 5. You're indexing numbers. So here we set I equal to 0, and while I is less than 10, we print I, and then we increase its value by 1, right? This statement looks kind of weird, but it's called like an increment statement, right? Because all that's happening is, if you remember your Python rules, that the single equal sign is assignment, and you read it right to left. What this means is it's taking whatever the value of I was, and it's adding 1 to it, right? And then it's storing that back in I. So if I was 0 at the beginning, I is not going to be less than 10, and that's when the while loop will end, right? So we'll see it produces this. Right? Because the 0, like 0 gets printed right at the very beginning.
Hey Jeff, could you repeat that?
Prints it, yeah. We saw it in lecture, but and basically, like if you just say you just had the while loop, actually the original programming languages only had while loops basically. It didn't have these things called for loops that we learned, but so say you only had the while loop, right? You would a pattern, a programming pattern is like the name for it. If you want to Google that you'll find yourself doing a lot is like, oh, I have a list and I want to go through the things in it, right? So in this case, it's like, oh, I have a list of countries and I want to go through them. What you'll see is like this pattern, right? Where you'll say, okay, list index equals 0, because I want to start at slot number 0 in the list, right? Now, while the list index is less than the length, right? While it's not at the end, oh, I'm stuck. Okay, cool. While it's not at the end, do something, right? So in this case, while list index is less than the length, the total number of things, take the current thing, right? By accessing, going into my list, and then remember the square brackets for a list says, give me the element in that slot, right? So we take my list, we get the element in the slot list index, and then we print item number list index is the thing, right? And then this is our increment statement we saw before. List index equals list index plus 1, right? So this is not really code you should ever write in real life because it's kind of gross, because it's like, okay, you're keeping track of this index, but you're only doing that because like you want to go through the list one by one, right? Meaning like you're not interested in this variable of like 0, 1, 2, 3, 4, 5 so much as the actual countries, right? That's what you wanted to print all the countries. So programming languages developers saw that people kept doing this, right? And like, for example, this can lead to a lot of errors because, for example, if you forget this line right here, the increment line, what do you think will happen? And the answer is, I did this like 5 times because I made these slides last night. And I accidentally did this like a bunch of times where I forgot this increment line. And what happens is it just will print item 0 is Afghanistan over and over and over and over again infinitely, and it'll crash your computer. It won't because Python's like smart, but it would if Python wasn't smart. Like if you wrote this in C, the programming language, yeah, it would literally crash your computer because it would just use all the memory. So yeah, the point being like, oh, why are we want to get rid of this whole index thing? Because like, let's just develop a loop that is like specifically made for looping over things in a sequence, right? So cool, that's the for loop. It says for element in a sequence, run the expression, right? So meaning like this just automates all the stuff we just did in that while loop, right? It takes everything in the sequence and one by one, it says, okay, the first time through this loop, element will be item 0. The second time through this loop, element will be item 1. The third time through this loop, element will be item 2, right? And then expression, meaning in the indented code, you do whatever you want with that element, right? Similar flowchart, which is one difference, right? Which is the update counter, because it's keeping this counter of where we are in the list for us. Whereas with the while loop, we had to do it manually and like manually write increment statements, right? So in this case, it's for each thing in X, do Y. That's why it's called a for loop. So in this case, like we can do exactly what we did before, but it looks so much nicer because it's just for current thing in the list, print the current thing, right? And it prints them all. And if we actually are interested in the index after all, right? Like say you want to be like, oh wait, I want to see what slot like Yemen is in, right? Python has this nice thing that will just say like, okay, it's a for loop, but I'll also give you the counter. And to do that, you just put enumerate and then the sequence. So like here, we just put my list, and then it just gives us things in the list. But if we do enumerate my list, it gives us 2 things, and we have to separate them by commas, right? So it gives us the list index, and it gives us the element of the list at that index, right? So then we can just write the exact replica of our while loop from before, but again, like we can control, right, based on whether we use enumerate or not, we can control whether we keep track of the index. Cool. So that's Python. Now, not Python, but you'll see it dovetails. It dovetails nicely. Very cool. Cool. So then this is the more recent lecture that Prof. Sperling gave. And it's about stats, but you'll see, we'll do Python stuff. And I know we have 5 minutes, but it's fine. We'll get through it. So sampling, the idea is just that we do statistics, right? Like the whole reason we do data science is because there are populations of things out in the world that we want to draw inferences about, right? Like maybe we want to see, right? Like we're like poverty, we care about poverty, and we want to like see what percentage of people in the world live in poverty, right? It would be very costly and probably impossible to go and find all 8 billion people in the world and like ask them if they're in poverty or measure their wealth or something, right? So yeah, like that's called a census, and we typically can't do it, especially not like in the world, right? In the US, we do a census, but even that's pretty flawed. But anyway, they do corrections. But sample is the actual set of observations that we have to work with, right? So sample is like, say, okay, I'm gonna go to every country in the world and I'm gonna randomly pick 100 people, and then I'm gonna measure their level of wealth or something, or their ability to get food or something like that, right? That's a much more manageable thing. You could do that with like a budget. So, but the point is, like, we're not just taking the sample because we're like, oh, cool, I really want to meet these 100 people in every country, right? I mean, it's cool, you can meet them. But the point is this arrow here, and that's why I like this picture, because it's like showing like, we want to like infer something about the population, right? So like this arrow is the key here. We're not just like interested in the sample for itself. We want to learn things from the sample and use it to draw inferences about the population, right? So just remember this like arrow here. You get lost in the sauce of like, why are we doing sample? Why are we doing population? The sample is just a thing that we do because we can't take a census. And then we use this black arrow is statistics, right? Statistics tools and techniques and shit is like, and stuff, sorry, is what we use to say like, oh, I think the average poverty in the population is like this or something, right? That's the stats tool. Like I took the sample of people and about 20% of them lived in poverty or something, but like I think I undersampled people in poverty. So then the black arrow is like you do statistical corrections and you say, okay, I think the real poverty rate is like 30% or something, right? You see the black arrow is like using statistical fancy tools to correct your sample biases, right? And then we talked about sampling with and without replacement. So going around the world, hopefully you would never accidentally sample with replacement, but when you're doing smaller populations, like say, like marbles in a jar, right? Like, you might like, if you take something out of the population, right here, this is a jar of marbles, that's the population, right? And we're taking things out of it to take our sample. We're taking 3 marbles out for our sample, right? But there's 2 ways you could take a sample of 3 marbles, right? One is called without replacement. What that means is you take something out of the population, you like write down its color, and then you throw it out, right? It can never appear in the sample again. But there's also sampling with replacement, which is where you take it out, you record the color, but then you put it back in the jar, right? So in that case, like you could get the same thing more than once. I know it sounds weird because like the example I use, it's like you would just see the person again and be like, oh wait, I already gave you this survey. No, I'm sampling without replacement. I already sampled you, so go away, right? But because not all like data sets and experiments and scientific projects are that straightforward, you might accidentally be like, oh no, we included like the same person or the same state or something more than once, right? And it's just something you have to do statistical corrections on, right? Meaning like here you're gonna think like, wow, there's a lot of purple marbles, right? But that's because like you're biased because you sampled with replacement. So it's like, oh, you saw the purple marble twice, but maybe it was only in there once, right? So anyway, that's why you have to do these statistical corrections, right? That's the black arrow, meaning like you say, oh, I sampled with replacement. And so some of these might be duplicates, right? And you have to do correction. Cool. We learned distributions where this starts to get a little weird because in the case of like poverty, I mean, there's kind of like no like theoretical distribution, right? There's no theoretical like, oh, this many people should live in poverty, right? As I think it's like Nelson Mandela said, like poverty is the invention of man and thus can also be cured by man, even though it's not just man, it's people. But I think this was like in the 60s or something. Anyway, point is like there's no like natural distribution of poverty, but for things like dice rolling, there is, right? If the die is fair, we would expect each side to come up 1/6 of the time. Or if a coin is fair and we flip it, we would expect heads to come up half the time and tails to come up half the time, right? So probability distributions are kind of like our expectation of what the distribution will look like, whereas then when we actually do the physical like sampling, right, we actually roll the dice or we flip the coin, we get an empirical distribution. And the point is like, for example, someone might say, hey, you want to gamble with me? I have, like, I'll supply the dice. And you'll be like, I think this person's kind of sketchy. I think they might have like loaded these dice so that they don't come up evenly on all the sides, right? So what you can do, right, that's like the classic thing in statistics is you can say, okay, the probability distribution that I expect is like each side will come up 1/6 of the time. Now, give me your dice. I'll roll them a bunch of times. I'll see the empirical distribution and I'll compare it with the probability distribution, right? If it's super different, there's probably something wrong with those dice, right? Because like say it just always comes up 6, right? They're probably trying to hustle you, right? So you can use statistics to not get hustled. Cool. So in this case, like, yeah, the distribution we would expect is the faces are 1, 2, 3, 4, 5, 6. The probabilities are all 1/6, and then I just plot them. I'm just showing you what it looks like. This is a probability distribution, right? This is not empirical. This is like a theory. This is what we expect. And then the law of large numbers says basically, okay, if the die is like actually fair, we can find that out in a way, because we can just keep rolling it over and over and over again and see if it matches the probability distribution we expect. So this graph right here is coin flipping, right? So it says excess heads over tails. So the y-axis is they're flipping coins and they're seeing like how many times heads comes up, how many times tails comes up, and they're just dividing them basically, right? And what you see is like with a few trials, right? If the trials are like, you do like 10 trials, yeah, you might get some weird stuff. Like you might get, oh, weird, I got 9 heads and 1 tail. So I'm kind of sketched out by this coin, right? I think you might have loaded it. But the point is if you do enough trials, if it's a fair coin, you do enough trials, it will eventually converge to 50-50, right? If it's a fair coin. If it's not a fair coin, it'll never converge to that, right? But the law of large numbers is like that property that allows us to differentiate, right? The law of large numbers says, if you do a bunch of trials, the empirical distribution will converge to this like theoretical probability distribution, right? The like quote unquote true distribution. In this case, fair coin, if you have a fair coin, the true distribution is 50% chance heads, 50% chance tails. And if you flip it 1,000 times, right? Each of these, sorry, I should have said each of these colors is a different coin, is a different fair coin that they just keep flipping over and over again. And yeah, you get, even though they all start off weird, because it's like, oh, I only flipped it 10 times. So this one gave a weird pattern. This one gave not a weird pattern, but you know, it's all over the place. But law of large numbers, you flip them enough times, right? You get a bigger and bigger empirical distribution. Or an empirical distribution with a higher and higher sample size. Eventually, it will converge to the true, quote unquote, true distribution of that sample size. Cool. So I just made a quick example here. You can look at the code, but it's just dice rolls, right? N equals 10, I'm using a NumPy function to generate dice rolls. And yeah, we're saying like, oh, yeah, this histogram looks weird because I only did 10 rolls here, right? I only did 10 rolls here. So it looks skewed. Here you're like, oh, I think maybe you loaded it so that it like comes up 2 way more often than any of the other ones, right? I rolled it 10 times and 2 came up 4 times. That doesn't seem right? But what you need to do is you need to roll it more and more times, right? So you increase n to 100. Here I started doing a while loop. You can, again, look at this code. And I did a while loop because it's got really tedious to like roll these dice over and over again. So I'm doing a while loop to produce these plots, right? So now it just produces 3 plots, whereas before I had to write 3 different pieces of code. Yeah, and here you're like, oh, I don't know. Like here, maybe you loaded it so that 3 and 4 come up more often than usual, right? Eventually, right, you smash the sample size increase button. Now we're rolling the die 1,000 times. We're like, oh, actually, it's starting to look more even, right? Again, I wrote a function, cool, learning what we used in Python. Wrote a function that just plots dice rolls for some sample size n. You can look at that. Now we roll the dice 10,000 times. It's looking even more even. 100,000 times. It's looking even more even. We roll it 1,000,000 times, and basically it just starts to be even among all the numbers, right? That's the law of large numbers in a nutshell. It's like, all right, I rolled your die 1,000,000 times, and the distribution definitely looks pretty even, right? Because recall our original distribution, it's this. They're all even, and yeah, that looks pretty good. Even though when we only rolled like 10, we might have been a little suspect, like, oh, are you weighing it to 2? So. All right, I'm 5 minutes over and I have a red battery, as maybe you can see, I don't know. It says 9 minutes remaining of battery. So sorry I couldn't do a Q&A at the end, but at least I got through all the slides. Maybe that helps. Yeah, great. Come to my office hours, email me, Piazza. I've actually been refreshing Piazza like a lot and just haven't seen anything lately, but just like know that I'm on there. And here, I'll stop the recording.
When do you think the test is going to be graded? Are you allowed to say?